I'm excited. So we're going to be talking about compounds now. And in this figure, I think this is from your textbook, we've talked about, we brought it up before. We said that matter actually has mass and occupies space. And matter can be either broken down as being pure or mixture. And if it's pure, we talked most recently about if you have a chunk of copper atoms, that would be like an element. Okay? But if those copper atoms are bonded to something else, like oxygen in a repeating unit, like copper 2 oxide or something like that, that would be a compound. So I was kind of thinking of grabbing a bottle of, because sometimes like, oh, chemicals, blah, blah, blah. Well, you eat chemicals. You know, we walk in chemicals. I mean, nitrogen is a chemical. You know, we're breathing chemicals. Have you ever heard that people have, that people every year die, a lot of people die from dihydrogen oxide overconsumption? Of course, dihydrogen oxide is H2O. You know, you can turn anything into something scary. I was thinking about chemicals, and I was like, just grab a bottle in your kitchen of something. And it's all spelled out in scary words. I really think that if they took the scary words and put them into like a chemical formula, it'd be like, ah, that's what that is. You know what I'm saying? I just think we, you know. So anyway, compounds. So a compound needs to have at least 2 different atoms that are joined together with a chemical bond. So one of the things that I want you to get out of actually this part is we're going to talk about those chemical bonds. Okay? So in other words, if I just off the bat draw an H2O molecule, okay, I'm not going to make you come up with how they're arranged, but I bet you buy this that we basically have a oxygen in the middle and 2 hydrogens branching off of that. So as I have these lines right there, those are both chemical bonds, chem bonds. Okay, they're both chemical bonds. Now in chemistry, there's different types of bonds that hold stuff together, but those are chemical bonds. Okay. So of course you know we use formulas, chemical formulas, to represent the molecule, or to represent, here in a minute I'm going to call them the formula unit. But basically a compound, we say what atoms are in that repeating unit by using their symbol, the little subscript of that type of element there are. So for instance, you know, we're all kind of familiar with, you know, water. One of my pet peeves, and I don't know if it's yours or not, is, I bet you've seen this, H2O with a superscript 2. Like, oh no, that's not how you do it. Okay, that's okay, but no, that's all right. So the subscripts, of course, say how many atoms of that type of element there are in that repeating unit. So with ethane, you know, we have 2 carbons and 6 hydrogens. Now, I want to draw your attention right quick to magnesium nitrate. Do you know, like in math, how, well, I don't know if it's math, but this actually, this 2 right here, that 2 right there, means that we have 2 of the NO3 groups. So that's one of the things I want you to kind of get a handle on. If I was going to kind of draw the structure of magnesium nitrate, it would look like this. We have 1 magnesium. By the way, we know we have 1 magnesium because there's like no subscript there. 1 magnesium. We have 2 NO3s. So here we go. There's one lone magnesium, and here's my NO3. Oops, I'll pick a different color. NO3 and NO3. There you go. Okay. Now, actually, that magnesium needs to connect with those NO3s. And my convention in the past, I'll probably stick with it, I'm going to draw, instead of a solid line, I'm actually going to draw a dotted line. My dotted lines are another chemical bond. They're just a different type of chemical bond called an ionic bond. So hopefully you can kind of see how all of those atoms are joined together in magnesium nitrate. Now, one of the things, I don't know, you might be tasked to do with on a test, wouldn't it be clever if I asked you how many atoms there are in a magnesium nitrate unit? So you count what? Let's see, these each have 8. So we have 8 sorry, so 4. We have 4 plus 4 is 8 plus 1 is 9. So there's 9 atoms there. Does that make sense? 9 atoms. To kind of unpack that formula. Okay. So this bullet right here, actually, okay, compounds can be broken down, basically, chop, 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 chop. It's kind of neat to think of. Sometimes it's just heat. Sometimes it's just heat that will actually break all of those chemical bonds. Okay, sometimes you need like a little enzyme in a biological process that kind of breaks a certain bond. Okay, so they actually can be broken down into smaller pieces, all the way down into their elements if you want to. All right. So chemical bonds, and here I brought an exercise today. Now we're not going to do it. I think we're going to do it coming up here about slide 14 or so. But you guys are going to actually look at joining a pair of atoms together. Okay, kind of like we saw. Water molecule has an oxygen bonded to 2 hydrogens. Those are chemical bonds. Now, chemical bonds come in 2 main types. Chemical bonds can be either molecular or ionic. And already I can see, actually this exercise this morning, I called molecular bonds, now this is a chemical bond, I called it covalent. So those are synonyms, covalent, okay? Molecular, covalent. So what I'm going to do is actually make like a tally here, a list of kind of compare and contrast. Okay. So let's see. Chemical bonds. That'll be the type 1. 2 types of chemical bonds. We have molecular. A synonym for molecular is covalent, and then we have ionic. 2 types of chemical bonds. Again, what are we talking about? We're basically talking about joining, and I just kind of say generic, atom A and atom B. We're joining them together, and that dash right there is the chemical bond. So right off the bat, we actually kind of have something to add here. So molecular or covalent bonds, okay, they create molecular compounds. Molecular compounds. And if you don't mind, I'm going to abbreviate compounds CPD. So anytime you see CPD, that's compounds. Okay. Ionic chemical bonds. If you have 1 ionic chemical bond, then you have an ionic compound. Okay. If you have a molecular compound, the repeating unit, I'll just say unit, colon, is a molecule. Everybody loves it. The word molecule is just adorable. Molecule. Okay. If you have an ionic bond in your form or somewhere in your compound, then your repeating unit is a formula unit. Okay, so we have kind of compare and contrast there. So let me go ahead and kind of, while we're at it, with regard to these 2 types of compounds, an example for something that only has molecular or covalent bonds is water, H2O, and I'll go ahead and draw it again. I have an oxygen bonded to a hydrogen, actually bonded to 2 hydrogens. And then an example for the ionic bond, ionic compound, is something that I should try to avoid more of. We should all try to avoid more of table salt. If I were to ask people just on the street, what's the chemical formula for water? They'd probably say H2O. What's the chemical formula for salt? They'd probably say NaCl. But in chemistry, actually the term salt is just kind of actually used more generically than NaCl. Okay, in general, any sort of ionic compound can be called a salt. So let's go ahead and draw that NaCl. Now here, when I draw the chemical bond between them, it's just my habit, I'm going to draw a dashed line instead of a solid line. So kind of the coup de grace here, and we'll talk about the differences between our molecular bond or ionic bond momentarily. But honestly, that dash right there, that type of chemical bond is an ionic bond. Ionic chemical bond, ionic bond. Okay? And both of these solid lines, they are a pair of molecular bonds or covalent bonds. So that's kind of what I like to, that's what I'm trying to say in the next few slides, okay? Something else we can go ahead and add to our tally here, and by the way, I'll take a screenshot of this tally and push it up under Twitter too. So something else to add to our tally is this. Remember we talked about the JAG on the periodic table. There's different ways to look at those elements, okay? Most of them are metals, and just a few of them are non-metals. Okay, and actually that kind of gets us down the road to identifying what's going on with regard, just given the chemical formula. We can get a sense for, is that what we call a, are there molecular bonds or are there ionic bonds there? So let's see, metals bonded with nonmetals produce ionic compounds. So down here on this right side for ionic, I'm going to put metal bonded to nonmetal. Metal bonded to, how's that? Dash, 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 dash. Nonmetal. So now here's where you're going to pull in, you guys did some homework kind of identifying, you know, look, you're given an element, like it's a metal, it's non-metal. Well, one thing then, actually we can know if you bond them together, what sort of bond or chemical bond you're going to get. So find the JAG and find sodium. Sodium is clearly a metal, okay? And of course the thing it's bonded with in table salt is chlorine. So chlorine is clearly a nonmetal. So sodium's a metal, chlorine's a nonmetal. So definitely it falls into this category. That it's an ionic bond between those two atoms. So nonmetals bonded with other nonmetals are over here. Nonmetals. Nonmetals, I'll go ahead and put a dash. That's my chemical bond. That's a molecular covalent bond. Nonmetals. Cool. One last thing, and actually we put it under this left column. If you're looking at a chemical formula like, I don't know what's going on, I have hydrogen. What is hydrogen? You guys remember on my periodic tables that I gave you that you'll have for your test, hydrogen appears twice? Like, really? Okay. So the one I gave you, hydrogen's over here, and also hydrogen is over here. No, it's not twice up there, it's just twice here. So hydrogen, for purposes of seeing it in a formula and kind of getting a sense for, well, is there gonna form an ionic bond or a molecular bond? Hydrogen is a nonmetal. It's not a non-starter, it's a nonmetal. Hydrogen is a nonmetal. Okay, so with that last little bit there, can you see where if we look at water, okay, oxygen, let's see, find oxygen. Oxygen's a nonmetal. And we're going to consider hydrogen a nonmetal, so we definitely have two nonmetals joined here. Now, why is that, okay? Well, we're going to come up with why that is. But let's take a look at all these and use these rules and say which is which. Another way to look at it is if you find a metal anywhere there, it's an ionic compound. Look for the metal. I'll go ahead and circle metal. If you find a metal, bada boom, it is an ionic compound. So let's see, water, I already said consider hydrogen nonmetal, so actually water is a molecular compound. So I'm going to put molecular there. So we're going to look for the metal. And to me, you know, don't be shy to look at the periodic table. Molecular. I'll go ahead at the top here, say compound, CPD, question mark. Okay, and then we'll say which one they are. That's a molecular compound. Carbon and oxygen. Okay, so oxygen is on that side of the jag. Carbon is also on that side of the jag. So we have two nonmetals. So again, it's molecular. Carbon and hydrogen are like, dude, okay, so carbon is a nonmetal, hydrogen is a nonmetal, so it's going to be molecular again. So calcium sulfate. Okay, find calcium. Oh, okay, calcium's a metal. So finally, it's looking like we have an ionic compound. We do. Let's skip to the last one. Okay, magnesium nitrate. And did you kind of notice how, like, with calcium sulfate, magnesium nitrate, the metal was written first? That's not by accident. That's kind of usually the way it is. So find magnesium, like, all right, magnesium. Yeah, it's in the part with the metals. So magnesium is a metal. Okay, so definitely it's an ionic compound. Okay, now I need to go back and revisit that ammonium sulfide. So the problem with ammonium sulfide is it's actually one of the exceptions. I wished I hadn't gotten it in here. Actually, this NH4 unit runs around with a charge. So this is actually ionic. I would not include, in case you're wondering, anything ammonium containing. I would not put that on the test. But that is an ionic compound. The reason, do you see why I'm saying this, is because if you find nitrogen, so if you're just going from left to right for all of the elements in that. Right, they are all in the nonmetals. But it is an ionic compound because actually ammonia is NH4, and it's running around with actually a plus charge. And as your sulfur, actually then I'm going to have to put two, no, I'm going to put one of them there, and actually I'm going to put two NH4 units. It's kind of something I didn't want to emphasize at this point. It's also plus one charge. This is a minus two. So dot, dot, dot. My point is that that's kind of how those, let's see, how many atoms are there? There's 10 atoms in NH4. So there's 11 atoms. So that's how those 11 atoms are arranged. So I'm kind of emphasizing something that I didn't want to necessarily cover right now. So that one snuck in there on me. But that's actually, those that red dashed line, that is an ionic chemical bond. Those solid lines, those are covalent bonds.
Can you hold that picture there for a second?
I can.
Kind of like OCD kicking in. Okay.
You're welcome. So chemical formulas. So we can actually do a little problem, and I'm gonna, if you have calculators, you can drag them out. But we're gonna come up with how much. Now, remember we have different names for the units. So we're gonna come up with how much a molecule weighs, like a molecule of water. How much would a molecule of water weigh? Right off the bat, you're like, remember we talked about, you can know how much an oxygen weighs from the periodic table. It's that decimal number. You can know how much hydrogens weigh from the periodic table. So basically, you just add all that together, and that's how much a water molecule weighs. Okay, so that's the sort of problem I want to do. So remember then that decimal number from the periodic table, it's in units of AMUs, which, like I said, I usually call it AMUs, but actually I'm trying to segue into calling them U's, the symbol U for AMUs. Okay, so let's do a problem. It's actually easier to show you. So if you have a periodic table handy, I'm going to use this periodic table. And you can kind of follow along or whatever. But at the top of this, when you see these on your test or for homework, I'm going to say show all work. And I hope you take me at my word. So if you get the right answer but you don't show all work, then I can't give you credit. So all I mean to say is this. So we're going to pick on water. So I'm going to go, actually, this is the way mine look. So I'm going to take two, and actually the first thing I'm going to go after is a hydrogen. So I'm going to take two times whatever hydrogen weighs, which is 1.008. Okay, and I'm going to take plus 1, because I only have one oxygen, times whatever oxygen weighs, which is 16.00. Right, exactly. I'm going to plug that into my calculator. And remember, I haven't really emphasized how you round, okay? But in this case, you're going to probably give it 2 decimals, which is right. Okay. So what I get is 18.02. So you have to show your work. And the other thing, and we talked about this in the physics unit, is you have to give it units. Okay? So the units are MUs, which is the symbol U. Okay? So that's how much a water molecule weighs. Does that work for you? I think they're kind of fun. Let's go ahead and kind of, like I said, I'm going to fill it out here, and then you can fill it out there as we go, and we can kind of check if you want to. They're kind of fun. So for carbon dioxide, we have 1 carbon dioxide. The decimal number for carbon is 12.01. And we've got 2 oxygens here, so I'm going to take 2 times the decimal number for oxygen, which is 16.00. And whatever my calculator displays, it will only give me 2 decimals. I'm going to round it to 2 decimals. Haven't done that one for a while. 44.01 AMUs. Ethane. I'm going to take 2 times the decimal number for carbon, which is 12.01. Plus 6 times the decimal number for hydrogen, which is 1.008. And I'm going to go ahead and round it to 2 decimals, 30.07. Somebody gets something different, let me know. Don't forget units, use. For calcium sulfate, I'm going to take 1 times the decimal number for calcium, which again, you're not going to have to memorize the decimal number or the atomic number, because you'll have this periodic table. Calcium is in 2A. The decimal number is 40.08 plus 1 times the decimal number of sulfur, 32.07, plus 4 times the decimal number for oxygen, which is 16.00. And I got 136.15. Now, the weight or the mass, actually we said those are 2 different things, right? Weight is actually the force of gravity acting on mass, but the fact that calcium sulfate is heavier than all of those other things, actually that's a property, that's a real deal. Actually, it can be used in its benefit. So the next one, ammonium sulfide. We have a few elements to add together there. So we need to look up the decimal number for nitrogen. Now, do you see where we have 2 nitrogens? We have 2 nitrogens, and how many hydrogens do we have? 8. Yep. So we're going to take 2 times the decimal number for nitrogen, which is 14.01. Plus 8 times the decimal number for hydrogen, which is 1.008, plus 1 times the decimal number for sulfur, which is 32.07. I got 68 point, I'm gonna go with 1.5. So for being complicated, it wasn't as heavy as calcium sulfate. All right, the last but not least. Okay. Magnesium nitrate. I'm going to go with 1 times the decimal number for magnesium. Now, magnesium is a metal, a 2A metal, and its decimal number is 24.31. Plus, how many nitrogens do I have?
2.
Yep, plus 2 times the decimal number for nitrogen, which is 14.01. Plus, how many oxygens do I have?
6.
Yep, plus 6 times the decimal number for oxygen, which is 16.00. And we'll see how she comes. Okay, I got 148.33. Pretty good. So that's how much those, now remember, if it's a molecular compound, we call it a molecule. So that's how much a molecule weighs. Or if it's an ionic compound, we call it a formula unit. So that would be how much the formula unit weighs. Any questions about that? So you have an assignment just like that. On page 361, exercise number 4. Heather. So that would do that. But one more thing then to kind of tie in this idea of chemical bonds is why those chemical bonds do what they do. Okay. So the nature of the chemical bond looks like this. It has to do with electrons. And actually I'm going to add a word to this where it says 2 atoms because their electrons are either being shared or electrons have been transferred. We talked about important electrons called valence electrons, so I'm actually going to insert that word there. Valence electrons. And I can't remember if maybe the homework you turned in actually had you look at where it was on the periodic table so you know how many valence electrons an atom has. So it's these valence electrons that are actually going to make these chemical bonds, okay? Valence electrons. So starting with the covalent chemical bond, so up here, I wish I had another color marker, that's okay. Up here where it says, I know it says molecular bond, but it's the same thing as covalent bond, sorry, molecular bond, covalent bond. But right here, electrons are being shared. So I'm going to try to kind of put that here. Electrons are shared. Right there, electrons are shared. Which electrons? Valence electrons. And so I'm going to go over here on the other side. Okay. Now there's a lot more to say about this poor chemical bond right here. But bottom line is the valence electrons associated with the sodium and the chlorine, I'm just going to say electrons are transferred. Electrons are transferred. Right there. So actually, we can kind of break it down. Electrons are transferred. I had a video, I don't have the video handy to show you. But basically an electron jumps ship, okay, and then it leaves a cation, something that is, an electron is going to jump ship from the metal to the non-metal. Okay, jump ship, electron. okay? And that's going to leave this positively charged, and that's going to leave this negatively charged. So electron jump ship, positively charged, negatively charged, and that that's because you have two things that are different charges. That's it. That's an ionic bond. So actually related to both the sharing and the transfer is this 8 up here. If you've kind of had chemistry before, you've heard of this. It's called a complete octet sometimes because octet is 8. But why do they share? Or why are they transferred? And it's because that atom wants to have 8 electrons, and it doesn't care if it had it to begin with or it gets it from sharing or gets it from transferring. Kind of a stepwise sort of thing. So, for whatever reason, in physical science, a lot of times we'll take an idea or a characteristic or something, and we will give it a Greek letter. Like, really? That's what the Greek letter is. Okay. But there's this thing called electronegativity. And electronegativity, negativity sounds bad. Electronegativity is basically, if you have two atoms, electronegativity says, how much does that atom want to bring electrons to itself? That's electronegativity. The electronegativity is bringing, how much does the atom want to bring electrons to itself? And the symbol for electronegativity is this Greek letter. It looks like an X, okay? So it just looks like an X with a fancy loop up there. That's electronegativity. Electronegativity, the atom wants to, I sometimes say hoard, like you hoard chocolate. It wants to hoard electrons. Electronegativity wants to hoard electrons. Okay, so that's on the next slide. Okay, so electronegativity is the attraction, the hoarding of electrons that an atom does when it's bonded to another atom. Now, some things in science can be measured, like measured, and this is one of them. So actually, we have some electronegativity values coming up to kind of show you for each element what's its electronegativity value. But the higher that number, okay, the more hoarding goes on. Gimme, 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 right? Actually, though, if I kind of turn your attention to table salt, okay, gimme, gimme, gimme electrons. Can you actually see the chlorine is like gimme, 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 gimme. It actually has what we call a high electronegativity. You see the sodium? It's like, take my electrons. It's got a low electronegativity. So I'll go ahead and put low. The symbol for electronegativity looks like an X. Low electronegativity for the sodium. High electronegativity for the chlorine. Yes, I do need different color markers. So here are and it was Linus Pauling, who I don't know what year it was, but he won, I think, a Nobel Prize for this in chemistry. But actually understanding if an atom's going to want to get electrons like chlorine or give them off like sodium. And actually kind of that pattern with chlorine, a non-metal, wanting electrons, that's kind of how it goes. And sodium, a metal, want to get kick off electrons. That's kind of how that goes. So here's the Pauling values. Notice it's not the whole periodic table, it's just a select part of the periodic table. These are your group A elements. So we have 1A, 2A, and then we have 3A through 6A, kind of after the little inset, the transition elements. So these are all group A elements. So generally speaking, metals have low electronegativities. Let's see, low electronegativities, low. Ugh, I don't want my electron anyway, okay? Non-metals have high electronegativities. So this slide actually might be helpful in the little exercise I'm going to turn you loose on here in a minute. Okay. Seems like, did we talk about, I think we did. Anytime you see this symbol that's a triangle, okay, triangle means change in. Maybe we didn't. I think we did. Yeah, because change in velocity is acceleration, so delta V is acceleration. Yep. So here at the top we have change in or difference in electronegativity values. Now, the thing is, I'll go back here one more. All you got to do, for instance, if you're bonding two atoms of two different elements, all you got to do is basically pull these numbers and do a little subtraction. That's your delta chi. That's your electronegativity difference. That's it. So if you do that subtraction, then actually you can kind of get a sense for kind of what's going on. Okay? If that difference is large, okay, an electron's going to jump ship. And here in a minute, I think I already had it on your, yeah. You can see already at the bottom there, jumping ship is about 1.7 difference in their electronegativity values, electrons transferred. Other than that, electron is shared. Okay, so all of these, electron is shared. But electron isn't shared, what we say, equally. For instance, a good example is water. Water's a great example. Let's pick on water and see how this goes. So we said water looks like this. Oxygen and hydrogen and hydrogen. Okay, now somebody who has great vision, let's pick off, this looks like 3.5. It's hard to see. But can you see the electronegativity of oxygen, 3.5? The electronegativity of hydrogen, 2.1. For each of them. Okay, so actually we could focus on, let's just focus on this left one. We could actually kind of look at that and come up with what we call the delta triangle, delta chi, okay, the electronegativity difference. And it looks like it would be 3.5 minus 2.1. And it's the absolute value of, so I just took the bigger one minus the little one. So what is that?
1.4.
1.4? Oh, good.
Now,
One-
would we put the wavy X thing after it? Or what would we do for units?
1.4 units, I don't think there are units for electronegativity. That's a good point. I don't think so. I think it's unitless. But 1.4 is the electronegativity difference between these two. So here's the deal. And which one's the greater? So oxygen has got a higher electronegativity. So the cool thing about water, and it's a player in why water does what it does, is the tug of war between those two atoms. Which color haven't I used? Actually, can you see where this one is actually what we say partially positive? And so we kind of make this little S symbol to say it's partially positive. So that's partially positive, and this one is partially negative. Your hydrogens are partially negative. And this hydrogen will also be partially negative. Excuse me. So for every, I'll kind of redraw a water molecule. Here's my redrawn water molecule. For every water molecule, and it is bent like that. It's like, really? Seems like it'd be a straight line. No, it's bent like that for a reason. For every water molecule, it actually runs around with kind of a little positive charge here and a little negative charge here. This actually is, we say water is really pretty darn polar. Strongly polar. It is. It's kind of neat, like, you may have seen the demonstration where you take like a trickle of water and you take a comb and you like put electric charge in your comb. You hold it up to the trickle of water and you can actually make that water move. It's responding to the charge in your comb. It's like doing that sort of thing. It's amazing. Water's amazing.
What about the other side of the water molecule? Why don't we subtract that side too?
for,
Since there's 2 hydrogens.
yeah, we could, the electronegativity difference here is 1.4 and this is 1.4. These 2 hydrogens aren't connected. So you're only looking at the chemical bond.
So just the one chemical bond.
The one, actually, we could have done the similar thing. They're both electronegativity difference of 1.4.
Right.
So it's 1.4 there, and it's also 1.4 there.
But since they all come into a compound, I just don't understand, like, since they all come into the compound, why you don't subtract both of them and then have that number as your.
Well, we can talk. I think I know what you're saying. I have
You
to,
know what I mean?
kind of, I think so. I think there's an answer to that, but, yeah. Before we move on, let's go ahead and do a similar thing with table salt. Okay, so table salt looks like this. Na dot 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 dot, and that's the chemical bond, ionic chemical bond, Cl. So let's look up on the table for sodium, and is that 0.9? So the electronegativity of sodium,
0.9.
0.9. And the electronegativity of chlorine,
3.0.
3.0. And let's go ahead and come up with the electronegativity difference, the triangle or delta chi, electronegativity difference. Let's just go ahead and subtract the small one from the big one. So 3.0 minus 0.9 is equal to 2.1.
Mm-hmm.
Okay. So in this case, the chlorine basically was so powerful in this tug of war. It's got such a high electronegativity that actually, kind of like what I drew over there, an electron is transferred. Out and out transferred. Okay. So if an electron is transferred, and like I said, it's kind of stepwise, and we'll be talking more about this in Friday's lecture, that ends up now with an electron transfer that becomes negatively charged. Okay. And this actually losing an electron becomes positively charged. And the reason then that unit sticks together is because the positive and the negative attract each other. Let's see, how do I show attraction? They attract each other. And that's your chemical bond. Okay, well, I think what we're going to do is the exercise I have for you, we're going to kind of, Friday we're going to take a running start at this, and then I'm going to turn you loose with kind of a little bit of an exercise. In the meantime, Thursday's lab is going to be, like I said, to introduce chemical reactions to you. So that's all I have. Right? Right.